Hello and welcome to our section 4.2 on area, and in this section we are going to talk about summation and some little new notation for us. So we have some new notation that we're going to be dealing with, and basically for this first one here they're asking us to sum I. And so we first need to talk about this thing, and this summation. Basically this is just taking a whole bunch of numbers and adding them up. Well, I is our counting number in this case, and so we're replacing I with 1 and then with 2, 3, 4, 5, and 6, and this symbol means sum 'em, so we're gonna say 1 plus 2 plus 3 plus 4 plus 5 plus 6, because we're summing the numbers from 1 to 6. That's what this summation and this symbol means, add 'em. So we're adding numbers 1 to 6. So if it's something like this is a little bit of a formula. We're going to say we're summing from 0 to 5, but if I put 0 in for I, 0 plus 1 is 1. If I put in 1, my next counting number, I get 2, so 1 plus 1 is 2. If I put in 2, I get 2 plus 1 is 3, and then 3 plus 1 is 4, and 4 plus 1 is 5, and 5 plus 1 is 6. And so that's as far as we're going, and you'll notice these two formulas, the A and B, are identical to one another, and so therefore you can use different summations to get the same values. Now this one is saying we're going to J is our counting number in this case, and we're going to be counting J squared, and so we're going to count from 3 to 7. So we're going to sum the numbers, but this time we're not going to just sum 3, 4, 5, 6, and 7. They're asking me to square each number as I do it, so I'm going to say 3 squared plus 4 squared all the way up to 7 squared, and that would be if I squared and added all those numbers up, that would be the value I'd get. So then where this becomes applicable is when we start dealing with something that looks like this. This is where we start getting things that you're going to start seeing. Well, 1 over n is a constant. There's a couple ways to deal with this. Basically, this 1 over n needs to be multiplied by every term that I get. So I'm going to say 1 over n, and this time I'm going to put 1 in for k, so it's going to be 1 squared plus 1. And then, okay, well, I'm going to say 1 over n again times 2 squared plus 1, just plugging in my counting numbers. It says go all the way up to n, and so I might do a couple more of these. But the thing is, I don't know what n is, so I just have to say, well, I'm going to continue all the way out until I get to n squared plus 1. And so then, unless I know what n is, I'm not going to be able to calculate any value for this. But this could give me a summation as we do this. And there's some value to this as we do it algebraically. We'll start using limits and things like that to help us. Other things you might see, this is getting into a little bit more function notation for us, is the fact that this x sub I might be some number, some fraction or some number that we're going to deal with, and therefore I could just say, oh well, f of x sub 1 delta x, and delta x will be a change in some values, and so I can just do this all the way up to 6, and that would be what I'm looking for. Now these x sub 1, 2s, and 3s are going to be some group of numbers. It might be a fraction, it might be hopefully a whole number. This delta x could also be a fraction or a whole number, and so then basically what we're going to use these for is this is how we're going to find the area of a rectangle under a curve. Now you may be saying to yourself, well, how is that going to work for this? The fact that these things don't look like that, well, f of x, remember, is a y value, and a delta x would be a change in x value, so then that would be length times width. And when you multiply length times width together, you get an area of a rectangle. And you'll see in my third example how that's going to work. So this is just the basic setup of how we're going to go through this. And so you need to kind of understand these things as we do it. Now, on this, though, let me back up a little bit. There is a little bit of a shortcut to knowing I and I squared, some formulas. And there's actually an I cubed and a constant term that we're going to talk about. So you might make sure you get these down. In your book, they're on page 260. You need to get these down. You need the summation formulas on page 260. So sum formulas there. And so the summation of I 1 to n of a constant is just the constant times n. That's one of the formulas we need. So if we take a constant and we're going to add it up 6 times, if I said this number was 3, if I was doing the summation from 1 to 6 of 3, then it would be 3 6 times. That's all it would be. If I am going to do the summation of 1 to n of I, which I is our counting number in this case, well, there was a famous mathematician that came up with this formula, and we can talk more about it in class. You can ask me when we come to class about it. But basically, he came up with this formula, n times n plus 1 divided by 2. That will give you the summation. And so if you look, if I take the previous problem, if I take 6 times 7 and divide it by 2, that should give me the sum that I have here. I believe this is, if I add them up, I believe that's 21. And 6 times 7 is 42. 6 times 7 is 42. And then you divide by 2, gets you the 21. So that's the summation formula for I. And then there's one for I squared that you could use. The summation formula for that, also in your book on page 260. Summation from n of I squared, which would help us for this j squared one, is n times n plus 1 times 2n plus 1. All divided by 6. And so I could plug in my well, the issue with this one is we're not going from 1 to 7. There's some work we'd have to do to get the actual answer for that. But we'll talk more about that in class also. So just hang on to these formulas. Make sure you know them because you're going to need them for when we get to class. So this first one here, they're asking us to sum from 1 to n of I plus 1 over n squared. And so they're saying, well, check the values at n, at 10, or 100, or 1,000, and 10,000. So what they're kind of getting at here is that we want to know what's happening as n goes to infinity. I mean, isn't that kind of what's happening? We're getting progressively larger numbers. So when we do limit as n goes to infinity, what are we looking for? Well, we're either looking for the horizontal asymptote or end behavior, or we're looking for basically where this function is getting close to. So that's kind of the idea of this problem, and so that's where the summations are coming from. And so if I'm going to evaluate this, I'm going to first go through and do a little simplification. I make my life easier. Any constant multiples, now this is just like anything else that we do. We can remove constant multiples. So n squared is a constant, and so it's 1 over n squared. So I'm going to rewrite this summation, which is exactly the same thing. Is I don't need to sum this constant over and over again right now. I could distribute it at the end, and I will get the same thing. So there's my summation with the 1 over n squared. It makes it a little bit better. And so then if I continue down here, I might be able to write my summation like this, because to make it more like the formulas you just saw, I might want to do something like this. The summation as I goes to 1 of n of 1 might make life a little bit easier. And so then continuing on, I have 1 over n squared. Now to get rid of the summation formulas, I go back to those formulas that I gave you on the previous page, that I was n times n plus 1 over 2. That's the summation from 1 to n. And then I'm going to add on, well, this is a constant, so I take my constant and multiply it by n. And that's basically my formulas that I'm dealing with for each one of these summations. So to get rid of the summations, that's why you need those formulas on page 260. Get those formulas. You need those. All right. So then, as I'm going along here, I can do a little simplification. I'm going to simplify the top up here, make this n squared plus n over 2, and I might want to make this one over 2 so I get a common denominator, so I multiplied the top and bottom by 2. And so now if I combine these guys together, I really have n squared plus 3n over 2, and when I multiply 1 over n squared in, I get something that looks like that. I might want to divide everything by 2. top and bottom, or divide everything by an n just to make it a little bit easier for you. So I get n plus 3 over 2n. Now that's probably the best simplification formula I've got for this. I might be able to do a little bit more, but this is probably going to be the easiest to plug in these values. So I'm going to go ahead and use this. Now it says if n is 10. Well, if I put n as 10, if n equals 10, then I end up with this summation becoming, looks like 13 over 20. So n over 10 becomes 13 over 20. N is 100. I get 103 over 200. If n is 1,000, I get 1,003 over 2,000. If n is 10,000, and hopefully you can see that that as I do this, the value is getting ever closer to a value that we could find with doing a limit to infinity, like I said. And so if n goes to infinity, this thing should be pretty darn close to a half. And so that's really, so limits, these summations, as you sum them out bigger and bigger, the number you get is bigger and bigger, the n that you're putting in, the closer you're getting to a limit. And so summations and limits kind of have a are kind of combined, are kind of related to one another in a kind of a strange sort of way. And so this next one, the reason why we're doing all this summation is because we want to find area under a curve. And so when we're talking about an area under a curve, and not a standard curve that like a circle or something like that, we have to come up with some way to do it. And the way we're going to find the area under the curve is to find the area of rectangles that either are under the curve or above the curve. And so when we do this, this area, hopefully you can see, will be less than the area of the curve, and this one would be bigger than the area of the curve. And if we kind of average these guys together, we might actually get the area under the curve. But what we're going to do here is we're going to find the area of each rectangle, and when we find the area of each rectangle, then that would give us kind of an approximation of what's happening under the curve. Now, one thing to think about is if I can make these rectangles infinitely small, then I'm going to get a better approximation each time, and we'll talk about that as we go along here. But so this time they're asking me to do 5 rectangles to find the area under the curve. So here's my curve. My equation of my curve is x squared plus negative x squared plus 5, and I'm going between 0 and 2. So I need to find out the width of my rectangles. So to find the width of, well, let's first talk about area of a rectangle. Area of a rectangle is length times width. Well, for our area, our length is, we're going to represent the length of the rectangle, the distance between each number, we're going to represent well, actually, let's rewrite this just real quick. I'm going to call this W times L, width times length. So if our length of our rectangle is, or the width of our I should have left it. It was. Anyway, if I have length times width of our rectangle is the distance between these 2 points. Well, that changes depending on how many rectangles we choose, how big n is. So in order to find that length, we algebraically or calculus-based call that delta x, our change in our x value. Well, our length is going to be our height, which is basically f of x sub I. So we're basically saying that however far over we are, this is our formula that we're going to use. So this is length times width. And so that is how we're going to find the area of our area under our curve. Well, the problem is we don't know what delta x is, but we can find it. Delta x is always found by taking the upper value, which is 2, and subtracting away the lower value. So we'll call this one B and this one A, so it's B minus A over N, the number of rectangles we want. So delta x is going to be 2 take away 0 over, we want 5 rectangles because they said up here there are 5 rectangles. So my delta x in this case is going to be 2/5. So that's the number that goes here. That's the width of each rectangle. And you can see, if you look at my drawing down here, I'll zoom it in a little bit, make it bigger, you can see that each rectangle down here is 2/5 when we basically is how we're dividing up from 0 to 2. So then how are we going to find the height? Well, in order to find the height, we would say, oh, we plug 2/5 into our function, and that would give me the height of this rectangle up up top. And that's how I'm going to find it. So if I'm going to say, oh, well, it's 2/5 over and up this far, this one is 4/5. And so instead of going through and doing each rectangle every time, we're going to use a summation to help us do that. And so we're going to sum from using 2/5. That's going to be our x sub I here. And then we're going to put in a counting number. So we're going to do a summation from 1 to 5, because we're using 5 rectangles, of f of, now the x sub I is going to be our delta x with an I tagged onto it. Whenever we're doing what we call right-hand sums, when the right-hand corners touch it, we're going to use this. And then delta x is 2/5. Well, you'll notice that this 2/5 I is my x value in my original function. So I've got to get rid of the f, the function of this, I have to rewrite it with our function that we have up there. So you're going to see this thing get a little funky real quick here. So there's my summation. When I plug in 2i over 5 in for x, I get negative 2i over 5 squared plus 5. That's that part. And then that needs to be multiplied. There's my height. And then I need to multiply by the width of my rectangles, which is 2/5. Now this is where the discussion of constant multiples came in from before. This 2/5 is a constant, so I'm going to move it out front of my summation, and I'll multiply it through at the very end. But right now, I want to try to get this thing as simple as possible, and so now I'm going to square this, which basically means I get negative 4i squared over 25 is that one squared, and then I'm going to add on, and actually I'm going to do this, another summation from I to 5 of just the constant 5. Well, now at this point, you'll notice that I have here, this 5 is a constant multiple, so I can just put an n after it to get rid of the summation formula. The I squared formula, unfortunately, I'm going to have to use the formula from the book that we know, and that's what I'm going to plug in. So I'm going to go ahead and rewrite this with that in there. The 2/5 is going to stay out front. And so then I'm going to do to get rid of the summation formula, I'm going to replace I with what it is. And so we have negative 4/25 times what I squared is. And I squared is n times n plus 1 times 2n plus 1, all divided by 6. So there's my I squared being replaced. And then this 5 is just 5n being added on. So now I get to simplify this a little bit, and with a whole bunch of simplification, algebra here, I can get this into some form that I could plug in 5 and for n, because that's the number of rectangles, and it'll give me the summation. You could actually plug it in here, and you'd probably be okay. If I multiply 2/5 times both of these guys, well, I'm not going to do that right this moment, but we'll just do a little simplification. And this is the tricky part again about this, is simplifying this. This is n cubed, and then we get, I believe, 3n squared and plus n. I believe that's what it is. All over 6, and then plus 5n. So I'm going to multiply through I'm going to multiply this through as best I can. See if I can get rid of anything like, well, okay, so this guy becomes 2n over here, because 2/5 times 5n becomes 2n, so that's 2n for that part. The 2 and the 6 this is 8 and 6 will cancel each other out for the most part. Well, not really, but the 8 and the 6 will cancel out a 2, which will give me negative 4 on top times n cubed plus 3n squared plus n, all divided by, that, not all of it, but just that first part, divided by 5 times 25 times 3. Alright, and so if I want to get a common denominator, I could, but I can go ahead and plug in 5 here. And when I plug in 5, I believe this comes out to be approximately 6.48 for the area under the curve. So then, the next one over here, same idea, but the problem is I am using the tops of my rectangles. The heights are these distances here, not the same distance as they were before. So what I'm going to do, my delta x is still 2/5. So delta x in this problem is still 2/5. That doesn't change. My width of my rectangles didn't change because I'm still using 5 rectangles. I'm still going from 0 to 2. The height is what's changing, and so this time the height of each rectangle is going to be 2/5 take away 2/5. So my x sub I in this case is going to be 2I minus 2 over 5. So basically I'm pushing the edge of the rectangle from being at the front back one, so that if I was to put in 1 here, which would be the first term, there's 1, 2, 3, 4, and 5, my 5 rectangles. If I put 1 in for I end up with being at 0. If I put 2 in for I, then it would be 2 times 2, which is 4, minus the 2 would put me back at 2/5. And so that's the whole reason. So this is now the formula. That is my x value that goes in my summation formula. So back to my summation formula like we did earlier from actually, I'll use the same one. My summation formula, this is the same as the other blue one over there. From I to 5, f of 2I minus 2 over 5 times 2/5. So height again, height in f, width in my delta x. So then my next one, when I kind of put it back into the function, this is where it's going to get kind of ugly, and you have to. This is where the algebra comes in. It's going to be negative, and then I get 2I minus 2 over 5 squared plus 5, that's just that part. There's my height of each rectangle pushed back, and then 2/5. And so I would then go ahead and do all my summation again that I did before. I'm going to square this thing, multiply it all out, and basically what ends up happening in this case is I'm not going to go through and do all that work. I'm going to leave that to you guys. But my summation from I to 5 comes out to be approximately of this thing 8.08. And so now I have these two terms. I have way too much, which I know. This is too much. This is too little. So somewhere in between, the area of the region is going to be between these guys, and that's really what we can do for right now is with this one. If we make these rectangles, like I said, infinitely small, then we will find out a pretty good approximation. So we're going to talk more about this in class. Please come prepared. If you have any questions, please see me and talk to me in class about these. Thank you.